Hey everybody, it's Mr. Patron, and in this video, we're going to learn about concentration. So we've been working through our solutions and acids and bases unit, and this video is going to be all about defining and calculating concentration of a solution. So I'm going to open up my slides, and as you can see in today's video, we're going to learn the chemical definition of concentration, so how it relates to chemistry, specifically with solutions, and how we can calculate concentration of a solution using two different units. And then, as per usual, you can use this guided notes Google Slides, shouldn't say Google Doc, or take the notes down however you want to do. And the video is going to have some questions in it, as per usual. Right, let's roll through this. So first off, what is concentration? So in the previous activity, you gave us a definition of concentration that was all on your own. But now we can kind of go through the chemical definition. So concentration is defined as the amount of substance that is in a specific defined space. And that's for really anything, like concentration of people in a space. We can use that kind of relationship here. But when we're dealing with the solutions in chemistry, we describe concentration as the ratio of solute to either the solvent or the solution. And this is usually in terms of either mass or volume or some other kind of unit that relates to either of those. Just a reminder, the solute is what we mix into a solution. The solvent is what the solute is mixed into. So like if we're mixing sugar into coffee, sugar would be our solute, where coffee is the solvent. All right. And then there are different ways that we can measure concentration, and they give us kind of like different numbers. And these different types of measurements lead to different quantitative descriptions or different calculations. So we're going to use two different formulas today. And just kind of state what concentration is in terms of something that's more concentrated compared to less concentrated. In general, a solution that is more concentrated has a higher ratio of solute to solvent or solution. A solution that is less concentrated would have a lower ratio of solute to solvent or solution. So in general, the more solute you have, the more concentrated your solution is going to be, kind of like a stronger concentration you could think of. Okay, make sure you jot this stuff down, and we'll move on. So what you're going to need to do is also get your reference table. So either have your printed copy of it or open up a new tab with your reference table. So just go to Classroom, you can find the link there, or just Google chemistry reference tables, and it should be like the first thing that pops up. And if you go to the last page, it is table T, you'll find that there are two formulas for concentration. And those are the two that we're going to look at today. So we're going to calculate concentration in terms of parts per million or in terms of molarity. So make sure you're able to spot those, circle them, highlight them, something like that, or write them into your notes. Okay. So now we're going to look at questions that relate to each of these two. We're going to start with the parts per million. So concentration in parts per million, or also known as PPM. So you may see that abbreviation. So a unit that we oftentimes use to calculate concentration is parts per million. And we'll often also see other iterations of this, and you may remember this from the reading about the Flint water crisis. So there's parts per billion, parts per trillion, stuff like that. So it just kind of varies based on how finite you want to get the number to look. But the one that the state focuses on in terms of our curriculum is parts per million. Now, this formula uses the masses of both solute and solution. And we typically use this for smaller concentrations, so like contaminants in water. And just something to keep in mind. Sorry, I was having trouble finding a pen to get it set. Okay, here we go. Okay. So just in terms of understanding what a solution is, remembering it. So a solution, we may recall, is a mixture of a solute and a solvent. So that's something that you're going to have to keep in mind, especially for this particular calculation, because when we're looking at a solution and its mass, we are incorporating both parts of it. So that's something to keep in mind. So in general, the formula for concentration in parts per million is the mass of the solute divided by the mass of the total solution, so it's solute and solvent, multiplied by 1,000,000. Now, if you were doing parts per billion, we would multiply by 1,000,000,000 or trillion, a few more zeros. But like I said, we're going to be focusing on parts per million in this class. So let's go through an example. So you are given 0.25 grams of sodium chloride, NaCl, and it is dissolved in 100 grams of solution. What is the concentration of the solution in parts per million? So once again, we're going to look at our formula. Parts per million equals mass of solute over mass of solution times 1,000,000, 1 million. So our solute, remember, is what we dissolve into the solution. Our solute is going to be our 0.25 grams of sodium chloride. And then our solution, it tells us we have 100 grams of solution. So we know where we're going to plug these in. So once again, our formula, PPM, is equal to our 0.25 grams of solute, NaCl, divided by 100 grams of solution. Doesn't specify what the solvent is, but we don't necessarily need to know. And then multiplied by 1,000,000. So you would just pop this into your calculator. 0.25 divided by 100 times 1,000,000 is going to get you 2,500 parts per million. So what this means is that if I had 1,000,000 particles of this solution, so combining the sodium chloride and the water, like those molecules, and I counted them up, 2,500 of them would be salt, NaCl. The remaining would be whatever the solvent is. Say it's water, it would be water. Right. So let's take a look at another one. I'm just going to clear this and we're going to move on. Okay. So this one says, suppose 17 grams of sucrose, so a type of sugar, is dissolved in 183 grams of water. What is the concentration of sucrose in parts per million? Once again, we have our formula, and let's identify our solute and solution. Okay, so we have 17 grams of sucrose is dissolved, so that is going to be our solute. And it says it's being dissolved in 183 grams of water. So here, water is actually not our solution, but our solvent. So here we have to think back and recall that a solution is equal to the solute plus a solvent. And this also relates to mass. So the mass of my solute plus my mass of solvent is going to be my mass of solution. So we have 17 grams of sucrose plus 183 grams of water. That means the mass of my solution is going to be 200 grams. Once again, solution is equal to solute plus solvent. And because we're stating specifically that the sugar, the sucrose, is dissolving into this water, we can recognize this is the solvent and not our solution. So we need to make sure we know the mass of the solution, not the water. So once again, we're going to just kind of star what we have. So we have our solute, We have our solution, and we no longer need this here. All right, so then let's just run it through our formula. So parts per million is equal to our mass of solute is 17 grams of sucrose divided by our mass of solution, times 1 million. Don't forget to do that part. And that should give you 85,000 parts per million. So once again, what this means, in our total mixture of sucrose and water, if I had 1 million particles, or 1 million molecules essentially, 85,000 of them are going to be sucrose, and the remaining would be my water. Okay. So there's some independent practice that's going to follow here. So we'll work through these two on your own, and then I'll go over the answers as well. Like I said, here are the two independent practice problems, so take a few minutes and do this on your own. Okay, so let's go through how we do these two questions here. So number one states we have 35 grams of ethanol is dissolved into 115 grams of water. What is the concentration of ethanol in parts per million? So once again, we have our formula is parts per million equals grams of solute over grams of solution. We know our solute is the ethanol. Sorry if I said methanol before, my mistake. So we have 35 grams of ethanol, but we are not given a mass of a solution in this case. So once again, it says dissolved into water. So we need to determine our mass of solution. Once again, we have our solute here, solvent. So we need to add them up. So 115 from the water plus 35 from the ethanol is going to give us 150 grams of solution. Multiply that by a million, and you should get your final answer of 233,333.3 repeating. That's parts per million. Now let's take a look at the second one. So it says a 900 gram sample of seawater is found to contain 6.7 times 10 to the negative 3 grams of zinc. Express this concentration in parts per million. So once again, our formula, parts per million is equal to grams of solute over grams of solution times 1 million. Okay. In this case, we do have our solution. So just to kind of be clear, the seawater is the mixture here. That is the solution. So we're scooping up 900 grams of seawater, and it's stating that inside of it is this amount of zinc. So we have both these values, don't have to do anything else with them. So let's get our 900 grams of seawater. And then we have our solute, which is 6.7 times 10 to the negative 3 grams of zinc. We can put that into standard notation. So we're going to move our decimal 3 places to the left. 1, 2, 3. So you should get 0.0067 grams as your solute. Times a million. And that will give you a concentration of 7.4 repeating parts per million. If you got any of these two questions incorrect, double check what you did or rewatch these parts of the video before moving on to the next one. Okay, so now we're going to take a look at molarity, which is another type of concentration using a different one. So I'm going to clear this. once again, another unit of concentration that is oftentimes used is molarity. So this specific unit describes the amount of moles of a compound in a specific volume of solution. So we see the formula here is molarity equals moles of solute divided by liters of solution. So once again, this is a volume, and moles we've learned about in our previous unit. Now, this particular unit is usually used for solutions that are made in the lab or for like kind of running larger chemical reactions. Again, parts per million, kind of looking at small things like contamination, where molarity we use in the lab when I say, I need a solution to make for this particular reaction. I need this specific molarity for it. Okay. So, and just a note, we use the abbreviation as M for a capital M for molarity, or also moles per liter. So those are just kind of a couple of different ways to look at the units. Now let's look at a couple questions. All right. So the formula for this one is a little bit simpler, as long as we have the right amount of information. So this question says, what is the molarity of a solution of sodium hydroxide, NaOH, if 2 liters of the solution contain 4 moles of sodium hydroxide? So we are looking for the moles of our solute. So our solute is going to be our sodium hydroxide, and we have here, it says 4 moles of sodium hydroxide. And then our liters of solution, it says here we have 2 liters of the solution. So this one's pretty straightforward. So we're just going to rewrite our formula. Molarity is equal to the moles of solute, so 4 moles NaOH divided by the liters of solution, which we stated 2 liters solution. This one, I don't think you'll need a calculator for. So 4 divided by 2, we would have a molarity of 2 moles per liter. Or you can say it as 2 molar, capital M. Make sure it's capital. Lowercase would be 2 meters. Okay. Once again, we just divided number of moles by number of liters. Okay. Let's go through a couple of questions now. All right, so this is some independent practice. So once again, try these out on your own, and then watch the video to go over them. Okay, so you should have done these on your own by now, and we'll check out how we did. So number 1, or it doesn't have a number, but we can say it's the first one, says calculate the molarity of a solution containing 1.2 moles of calcium carbonate in 1.22 liters of water. Okay. Once again, our formula is molarity equals moles of solute over liters solution. So our moles of solute, we have 1.2 moles of calcium carbonate. And it says that a solution of this amount of calcium carbonate in 1.22 liters of water. Now, I know in the previous questions, we were kind of looking at water as a solvent, but we are, given that we're using our moles of calcium and not masses in this case, we assume that the volume is consistent. So if you see liters of water compared to solution, for molarity calculations, they're pretty much the same. But for the parts per million, that's where there's a difference. So you would pop this into your formula, or into your calculator, I mean, and you should get a solution of 0.98 moles per liter. Let me just rewrite this, I'm sorry, got a little messy. Once again, 0.98 moles per liter. Okay. Next one is a few more steps. So it says calculate the molarity of a solution containing 51 grams of NH3, it's ammonia, in 0.75 liters of water. So here we are not given moles, but we know how to do this. We know how to go from grams to moles. using our mole conversion formula. So let's just remind ourselves of that. Number of moles is equal to given mass over gram formula mass or molar mass. Sorry, brain fart. So we can determine the gram formula mass of NH3 ammonia to be 14 from N, and I'm just rounding to the nearest whole number here, and then 1 times 3 for the hydrogen. So 14 plus 3 is equal to 17 grams per mole. So to determine our number of moles, we get X moles equals 51 grams over 17 grams per mole, which gives us 3 moles of NH3. Okay. I'm just going to block this off. So we now know we have 3 moles of ammonia. Now, once again, our molarity formula is equal to moles of solute. So here we have our 3 moles NH3 over liters of solution, which in this case is 0.75 liters. 3 divided by 0.75 is going to give us 4 moles per liter. So that is the concentration of this solution in molarity. Okay. If you got any of these questions incorrect or want to take a look at them, feel free to repeat this part of the video. And we'll take some more time this week to do some more practice with this. All right, reach out to your teacher if you have any questions, and have a great rest of your day. Bye.